What I would like to do this morning is, first of all, steal a good chunk of the thunder of everyone else that's going to be on the program today. I'd like to give you just a bit of a general overview on the topic of how to build a good road. And I don't want to try and teach a whole course in highway engineering here in 55 minutes time, but what I would like to do is to at least accomplish more or less an introduction to the topic, talk a little bit about some of the key aspects of the basics of road engineering, and perhaps, if nothing else, leave you with some things that might lead to some good questions for the rest of the speakers during the course of the day. Let me start by leading you over a road that I was involved with not too long ago. This is a road that has kind of an interesting history. I will fess up from the very beginning that this road is in New York, so no one needs squirm in their seat that this problem happened to them. But here we are, and imagine yourself, I tried to take these photographs from about driver eye level going down this road. We would typically, in my state, be permitted to go 55 miles an hour down this road, and the photographs are taken approximately every 50 feet. Hank, actually, well, maybe somebody else will need that light, but I think I can get by without it. Well, still going to have to get by without it. Okay. First interesting thing that happens right here, which you can see in the daytime, but not so well at night when the problem occurred, we crossed a jurisdictional boundary. And the agency that we're standing in, the town that we're standing in, believes in centerline stripes. The next one does not. Perhaps you get a picture that there's some trees in the distance there. Can you imagine coming down this road at 1 o'clock in the morning on a November night, 1 o'clock in the morning, but on a November late Saturday night, early Sunday morning in November, when there's a bit of a mist that has been falling all evening, the road is wet. You are 4 girls in a car. You have been to a couple of bars, but of course this testimony later indicated no one was drunk. As they come over that crest in the hill, now I'm taking these photographs every 50 feet, and the projector doesn't back up. Yes, it does. Okay. Notice the telephone pole on the right. That's just to keep me honest here as far as time is concerned. There's that same telephone pole. So you see about how far we're advancing each time. Notice how quickly the crest comes up on us and the curve to the right appears. 50 feet, nothing at all. A very shy 50 feet. Suddenly the curvature begins to become more apparent. That's only about 25 feet. And another 25 feet, the road ahead is visible to us in the daytime, but not at night. We go on down the hill and look back up. Notice over on the right how the outside of that curve is accompanied by a very steep bank. The steepness is not entirely evident, but it's about a one-on-one side slope. And you'll notice that there's a little clearing right here. There's a bush there, and there's a clear area right down that embankment right there. And that's where the car that night ended up, over the side and right down there, maybe 20 feet below, nose into the ground, and somebody wound up a quadriplegic as a consequence of that. That curve and its design cost the residents of that township about $200,000. And if there's anything that I leave you with today, it's a feeling that there's an overall concern for safety associated with what it is that we do in terms of road engineering. There are 4 primary concerns or considerations in road design, road building, road maintenance, road engineering in general. One of them is a concern for capacity, which for those of you from the rural areas are going to find that's not too great a problem, and I'll show you why in a minute. The geometrics or the design, both in terms of vertical alignment and horizontal alignment, are extremely important and can make the difference between whether a road is safe or not. And there are some associated aspects of geometrics that we'll talk about as well. The film that we just saw made the point that drainage is extremely important. I remember a saying from many years ago that the three most important aspects of road engineering are drainage, drainage, and drainage. And I think I don't want to steal the thunder of the people that are following me, but we're going to talk just a little bit about how that relates to successful road design. And then finally, the surface. And by pavements, I don't limit myself, excuse me, Bob Joubert from the Asphalt Institute. I don't limit myself to blacktop and Portland cement concrete. I think of pavement for low volume roads as also including good gravel as well. So we're going to talk a little bit about pavements. By the time we get done, if there's anything left for everybody else to talk about, I don't know what it'll be. They can all say it again. Now, the concern for safety is kind of a curiosity. I did a survey, a nationwide survey, of what are the critical issues that local roads officials perceive around the United States a year ago. And it was interesting that not one official came back saying that highway safety was a critical issue. I don't think that means that local roads officials aren't concerned with safety. I think what it means is that they see safety as an important integral part of all road engineering. And I want you to note, though, that the gates are open there, and there's always room for a few more. And we don't want to enhance this too much by the way in which we build our roads. Well, let me talk briefly about capacity considerations. I suppose it would be nice if all of our town roads could be built like this. There would be no capacity problems, there'd be no geometric problems, we wouldn't have head-on collision problems. But the realities of the matter are that we can't afford the couple $1 million per mile that this kind of road design requires. Capacity, or the highest capacities of roads, are achieved in designs like this, where the side friction in terms of driveways and so on are minimized. We concentrate access to a few limited points. There are many reasons why this is a good road, but let's face it, folks, we aren't going to build all of our local roads to this kind of standard. More commonly, what we see in the local road environment is either something that looks like this, fairly narrow, this one's paved, has some decent shoulders, there's a ditch there if you dig through the grass deep enough, and looks like a road through the backwoods. Capacity of this road is not high, but neither is the demand for traffic demand, so it's generally not too much of a problem. By the time you get to this kind of a road, and this is also pretty much of a good example of a decent quality local service road, capacity would be extremely limited. What are we talking about? By capacity, we're talking about the traffic volumes that can pass per hour or per day down a given roadway. One thing that you can see from these numbers is that when you're in a freeway or a multiple lane kind of a roadway, 2,000 vehicles per lane per hour. With 6 lanes, we're talking about 12,000 vehicles per hour. That's a lot of vehicles. If we translate that into passenger vehicles per day, recognizing that roads aren't fully utilized all day long, we're talking about numbers upwards of 80,000 vehicles per day. Is there anybody in this room that has to deal with those kinds of quantities? No, I don't think so. 800? That still is a pretty high volume road in a local jurisdiction. 4-lane road, 50,000 vehicles a day. A 2-lane road, you can still carry up to 13,000 vehicles a day under ideal conditions. And ideal conditions would be at a speed in the order of 25 to 30 miles per hour. It would be with limited access. It would be with no problems whatsoever alongside the road. But when you have a road, say in an urban area like this one, driveways, slums, McDonald's, so on and so forth down the road here, parking alongside the road, very small gaps between vehicles, quite a directionality, more traffic going this way, not so many vehicles going the other direction. All of these factors interact to reduce the number of vehicles per hour that you can get going down a road. One of the things that best disrupts traffic flow is stop signs. Everybody has to stop, so there's some portion of the hour when the vehicles are not moving at all. And you can see an instance in this particular example, this being in an urban area, where we have a road that's operating well in excess, the demand is well in excess of the capacity, and you can recognize that kind of a problem by the fact that vehicles queue up and can't pass through at the desired rate. Most town roads don't have that problem. If we take into consideration the realistic situation, that 13,000 vehicles per day, 2,000 vehicles per hour, drops down considerably. With the high design standard, and I'm going to define that in terms of geometrics in just a minute, but a good quality, perhaps state highway kind of a road, at reasonably low speeds, you could perhaps, under realistic conditions, get 1,500 instead of 2,000 vehicles per hour. With a low design standard, like that perhaps paved town road that I was showing you a second ago, the capacity drops off to 660. If you want to increase speed, then the number of vehicles per hour diminishes because the headway, or the distance between vehicles, increases. And by the time you get to a low volume road, it becomes somewhat difficult to talk in terms of the capacity of a low volume road at high speed. I won't iterate these details. The point is that increasing speed and increasing design standard, and decreasing design standard causes a reduction in the capacity of a road. But where we're talking about roads that have to serve 50, 100 vehicles per hour, capacity is not generally a problem. There's one that didn't drop, but we won't worry about it. We'll just keep on going. Now, there are ways in which we can improve upon the design and the capacity of a road. Eliminating slow-speed curves, for example, is one of the considerations that would improve upon the capacity. And let's talk in terms of design standards. And I'm sorry, I must apologize for this slide. It didn't reproduce as well as I hoped it would. Let's define what we're talking about here in terms of various types of highways. I think the slide that didn't drop was the slide that said we were shifting gears from talking capacity to talking geometrics. Anyway, in terms of design standard, we're probably talking anywhere, let's say, 16 to 20 feet in terms of a paved or central surface, with maybe desirably 5-foot shoulders, maybe anywhere in the range of 4 to 8 alongside the road. It would be nice if we had a right-of-way that was on the order of 4 rods or so, but seldom is that always available. The point is that you need some space alongside the road for ditches. And so this would be what we would typically call a low type or a low standard local access kind of a road. In terms of geometric design or cross-sectional design, an intermediate standard would perhaps have anywhere from 10 to 12-foot lanes, would perhaps have 8-foot shoulders, would have enough space for a good drainage ditch, and in order to have that enough space, you need on the order of an 80-foot right-of-way. That's probably getting well beyond the standards that most local roads in the Northeast actually have. But this would perhaps be a collector level of road, while the previous one would be what we would call a local road. Now, when we get up to the state highway kind of a road, where we would definitely have 12-foot lanes, we would like to have 10-foot shoulders. You need 44 feet, almost 3 rods, just for that. And you'd like to have 25 feet or so on each side for drainage purposes and for control of roadside access. So we get up to needing 100 feet or so of roadway right-of-way. Now, in terms of the elements of design, and I don't want to belabor this, let me just quickly run over the categories. I realize that it may be a little difficult in the back to see all these different things. The thing I want you to understand is that there are some prescribed standards for the design of a road. And those are prescribed in terms, beginning in terms of the design speed. What speed do you wish to be able to attain on the road? And then, as a function of that, the stopping distance increases with speed. The passing sight distance, or passing distance, increases with design speed. There are other considerations. For example, the minimum curve radius, and that would be a function of the cross-sectional superelevation. The maximum grade that we would like to have, and generally speaking, in the Vermont area, we would probably speak of it as being rolling, not mountainous, not flat. We try to avoid zero grades for drainage purposes. And all of these kinds of things are available in design standards which are published by agencies such as the American Association of State Highway and Transportation Officials. One question that I was going to ask earlier, and I think it would be good to ask it anyway, how many of you have in your offices, on your desk, use every now and then, any of the design standards of the American Association of State Highway Officials? Can I see a show of hands there? 1, 2, 3 that I see. How many of you have a book called the Manual of Uniform Traffic Control Devices? Aha, a few more there. Okay. How many of you have books on pavement design? A few. Okay. All of these kinds of things would be very, very helpful to you. And in terms of road surface, how much cross-section and slope you need is a function of what it's paved with. But typically, we need 1/8 to 1/4 of an inch per foot for asphalt concrete. Gravel would need quite a bit more, anywhere from 1/2 to 3/4 of an inch per foot. And turf shoulders, for example, need to be sloped quite a bit in order to get good drainage. Here's an example of a road that looks pretty good. It's signed, it's got drainage ditches, it's got a reasonably smooth surface that you could travel down without too much problem, mowed shoulders and so on. Perhaps if there's any problem with this road at all, it's the fact that the crown, the cross-sectional crown, is a little bit too flat, and that will lead to problems of deterioration in the springtime. Another geometric consideration, and I'm going to make the contrast between this as perhaps a good-bad example. Here's a relatively narrow bridge. My son is standing in front of the bridge parapet there, not at all well marked. On a dark night, somebody could, with that curve right there, could wind up being guided right into that bridge head wall, and it would stop them pretty fast. By contrast, here's a much better way of dealing with this. These are both local, low-volume roads, town-level roads, narrow bridge sign, some hashers to show the traveling public where the edge of that bridge is. Notice that the pavement is wider than the bridge, and that's a real problem. It would be nice if we could afford to have some guide rail that would go in there, but that starts getting pretty expensive. This is a fairly inexpensive way to head off a geometric design problem, which is how do you get traveling public going down a reasonably decent, maybe 18-foot wide paved traveled way through a narrow bridge, recognizing that we don't always mow the grass on the shoulders where it's visible, recognizing that everybody doesn't travel in the daytime, recognizing that if somebody runs into that bridge parapet, they're in big trouble. The use of guide rail is another aspect of geometric design. Sometimes it's really warranted to do so, where you have a big drop-off on the side of the road, as is the case here. And notice, this is a gravel surfaced road. There's no prescription that says you can only use guide rail on a paved road. Center line striping is another consideration, and believe it or not, and this comes directly out of the standards of the American Association of State Highway Officials, there are some circumstances under which the recommendation is don't put a line down the middle of the road. You probably would expect, if I think I asked you to begin with, you would expect me to tell you that you should always put a line down. That isn't the case. When you have relatively wide roads, or regardless of the width of the road, but relatively high traffic, you wind up with a situation where you should apply a center line stripe. As the width of the road diminishes, or as the level of traffic diminishes to where you're less than 16 feet, which are many local roads in New York and Vermont, the recommendation of the American Association of State Highway Officials is do not stripe. Can anybody explain to me why they say that? Why? I hear a sure. Why? You don't want to put a stripe down the middle of the road and then encourage people to drive with one wheel off the road, right? So by the time you're down to 16-foot traveled way, you've got an 8-foot lane, and that's getting pretty narrow, pretty hard to hit. So that de facto what's going to happen is people are going to drive on the other side of the stripe anyway. And so there are recommendations. Now, if you know these things, and if there is a problem, and you get hauled into court, or you have an irate property owner that comes in, and you can reach over on the side of your desk and pat on a book or open it up to the right place and show them that, in fact, the recommended standard is to not put a center line stripe down the road, it's really handy to know that kind of thing. Now, there are circumstances in that table where you should have a stripe down the road. This is one of them. Fairly good design, paved shoulders, perfectly wide road, but no stripe. Not good. You don't want, you need to be aware of the standards so that if something bad happens on this road, you can avoid winding up having egg on your face if you do have to go to court. This is a pretty good example of one where the lanes aren't too terribly wide, but the traffic levels warrant putting the stripe on the road. And I don't know how well you can see this in the back, but here's one that I really hate to see. If you look carefully in this shadow, you can kind of pick up the fact that there's a double no passing stripe in this road right here. If you ever want to wind up really having egg on your face in court, it's a situation where you have a center line stripe, but you fail to maintain it. There's no way in hell that anybody on a wet night could see that this is a recommended no passing zone, because the paint line has been allowed to deteriorate too badly. And so what happens here, somebody pulls out to pass, somebody comes over that crest, there's a head-on collision, maybe nobody is killed, but they get seriously injured, and you wind up in court. So when you do put down stripes, then it's incumbent upon you to maintain them. Railroad road crossings, grade crossings, is another one that's receiving quite a lot of attention now. You don't have to have a main highway to need to have some kind of an indication that there's a railroad crossing, so that people are alerted to the fact that this is a situation. And many, many accidents occur at railroad grade crossings. This is not necessarily a good example of a railroad grade crossing in terms of its signing and so on. And signing is one part of geometric design. But nevertheless, an attempt has at least been made to alert the fact. And you can imagine how difficult that would be to see if there was no sign there. Railroad grade crossing. Let's go on to the topic of drainage. I hope that I leave you a little bit frustrated, because my intent here is not to, as I say, give a complete course on these things, but simply to kind of give you an overview. Note the sign, weight limit 2 tons. I'm not sure I could legally drive across that bridge with that Jeep. And there's many, many of these around the country. They're not just in Vermont, they're not just in New York, they're all over the United States. The numbers are very large. The problem, why that is weight limited at 2 tons, exists right there. You see that crack? I'm not sure I want to drive over that bridge with that Jeep. Doesn't that look like railroad rail to you? Curious. That bridge had been there for the better part of 75 years. Its time had long since come. Let's be realistic with one another. At the federal level, there is a great deal of publicity right now about the problems of deteriorating infrastructure, the problems of deteriorating bridges and deteriorating highways. Let's not kid ourselves. We are not going to be able to afford to replace the 175,000 deficient bridges in the United States. We're going to have to bite the bullet and close some of these bridges and generate in the process some circuitry of travel for a few folks. But we're not doing them any favors in many respects to leave that bridge open, because sooner or later some jockey on a fuel oil truck who wants to save himself 5 minutes of travel time is going to go across there, and you know what's going to happen. He's going to wind up in the drink. So I think we need to recognize that from a policy point of view, we really can't afford to replace all of the deficient bridges in the country. Now, we talked drainage. Many people think of culverts and bridges and things like that when we talk drainage, but there's another kind of a drainage that's very, very critical, and that's road surface drainage. Water is bad for the people and the pavements, people driving on the roads and the pavements. On the pavement, if it can sit on the surface in ruts and puddles, it'll cause hydroplaning, which is dangerous at high speed. It can freeze, which of course causes skidding. Worse yet, as it circulates beneath the pavement by trickling in, it can soften clay bases, it can freeze to cause frost heaves, and if there's anything that you carry away today, it's one of the key features of successful road building is to have good drainage. Does that look familiar to anybody? Got a few of those here in Vermont? I suppose I should have disclosed a secret that I didn't put into that introduction sheet that Hank read. I lived in Quechee for a while, and if you recognize any of these slides, some of them I purposely put in here because they came from not too very far away. This isn't so great. Look at all the water that's collected in this wheel path right here. That night, there's snow on the ground. It's probably going to drop below 32 degrees. If there's insufficient salt in that water, it's going to freeze again. Even if there is sufficient salt and it gets cold enough, it's going to freeze again. And sure as Pete, somebody with a couple beers under his belt is going to come riding down this road at about 75 miles an hour in their brand new, just reclaimed and rebuilt GTO muscle car. Hopefully not my son. And that tree is waiting for him. Something else behind me is waiting for him. Having water standing on the road is inherently dangerous. It's bad for the pavement. Sometimes you call these things frost boils, eh? You see the water standing on the shoulder of the road. In fact, the shoulder of the road used to be over here, but gradually over the years, the road has deteriorated to the point where there's only a little bit left in the middle here. Unfortunately, we have altogether too many pavements in this kind of condition in the Northeast. There are three aspects that you need to have that kind of a situation occur for frost heave. You need to have prolonged freezing weather. We're very fortunate in the Northeast in that we do have prolonged freezing weather. You need frost-susceptible soils. We've been helped by Mother Nature. She slid some glaciers over us, ground all that rock up into a flour called silt, and we have frost-susceptible soils everywhere. You need water. All over the Northeast, we seem to be in a humid climate except this summer, and there's abundant water 10, 15, 20 feet below the surface. But if we can get rid of any one of these three, frost heave will be no problem. If we can get rid of the water, if we can get rid of the frost-susceptible soil, there isn't much we can do about the weather, but we can work on those two. And of the two, the one that I think we can do the most with easily is to get the water off the surface of the road. We drop to aggregate roads. This is a springtime aggregate surface road, pretty good road building material, but look at all those little potty critters there. Some people call them chuck holes, some people call them a pain in the neck, but there's clearly a maintenance problem here. We did some research a few years ago and came up with something kind of interesting as to what causes those kind of problems. Now I'm going to get a little technical for a second here. Cross slope, this is in terms of foot per foot, but 1/100th of a foot per foot is about 1/8 of an inch per foot. So here's 1/8, 1/4, 3/8, 1/2, and so on the aggregate surface road. This is the cross slope. This is the longitudinal grade. 1% grade, 2% grade, 3% grade, 4% grade. If you'll notice, down here in the lower corner of the diagram, we have a severe problem of pothole, or a definite problem of pothole severity as a function of what kind of a cross slope and what kind of a longitudinal slope we have. If we can crown the road and get out here beyond 3/8 of an inch per foot, and you remember from a slide a while back, the recommendation was 1/2 an inch per foot at least, or beyond this out here, the problem drops off to a trace, and then finally we're in the range of trace to none. And if you get way out here, 4 or 5/8 of an inch per foot, 1/2 an inch or more per foot of cross slope, or beyond 4% longitudinal slope, there's no problem of that potholing that you saw in the previous slide. This sort of thing. It goes away. So maintaining the cross slope is very important. Now you might say, okay, where I've got longitudinal slope, I don't have to worry about cross slope. Well, you do and you don't. What that slide doesn't show is that if you have no cross slope, but you do have longitudinal slope, you're going to get problems of rutting in the wheel paths. So you still need the cross slope, the crown, on an aggregate surface road, despite what the longitudinal grade is, to shove that water off to the side of the road. If you do that, you won't have problems like this, and you won't have little chuck holes like you saw in the preceding slide. You can maintain that cross section. Now you can have too much drainage. This road serves as an example. It doesn't look too bad here. In fact, it looks pretty doggone good here. It's a fairly narrow shoulder. Couldn't hardly park on it. What you can't really tell is how deep that ditch is there. Somebody got themselves a brand new grade-all, and they decided they were going to go out there and ream that ditch. And so they did. A few days later, somebody, in fact, I think that was a local septic tank contractor, I don't know whether he turned his head to look at a bird or what, but as he was going down the road, one wheel of that tractor got off the side. Before I could get down to my office and back with a camera, the only thing I could see when I went by there was this one big wheel sticking up horizontally. And the whole tractor was swallowed in the ditch. Before I could get back, they had brought this cherry picker out, and if you look carefully, there's a cable holding that up. And if you look at it from the back side, you can see how very far down in there they were, clear down there. And now they've got the hydraulics on and trying to push the darn thing out of the ditch. Well, it's not still there, so obviously they got it out. The problem that I'm trying to point out here is you do want drainage, but for heaven's sakes, don't put in a 4-foot ditch when all you need is a 1-foot ditch. You can have too much as well as too little drainage and create a hazard in the process. It makes good sense to have trash racks and to protect culverts so that when you get Hurricane Agnes, or when you get that key thunderstorm in the summertime, you don't wind up with a situation where just at the key moment when you need the capacity of the drainage facility, it's lost because a tree floated down there, or a few dead cats, or some old garbage cans or whatever, and plugged up the entrance to the culvert. The last item on the list is pavements. Why do we put pavements down? So that they will cause lots of problems for the highway department. If we didn't have pavements, just think of how much of your life would be pleasanter. Wouldn't have to plow snow, just roll it. Good old days. Well, there is a purpose for pavements. Primary purpose is to distribute surface loads over otherwise weak or seasonally weak subgrade soil. We put pavements down to prevent or reduce infiltration of surface water, again, to maintain the all-weather feature of the road, and to provide a smooth riding all-weather surface. These guys are what we design pavements for. The automobile behind is like a pimple on the nose of an elephant by comparison to the stresses that are created by this guy right here. Big, heavy trucks cause essentially all of the fatigue damage to a road. Have any of you ever sat absent-mindedly, bent a paperclip back and forth in your hands? You know what happens. Show of hands. That's good to exercise the arms. How many of you ever bent a paperclip back and forth? I better ask the other question. How many of you have never bent a paperclip back and forth? Okay. You've done it. Now you can bend that dude back and forth 3 or 4 times, fold it back into position, clip it onto your papers, and everything's copacetic. You do it another 2 or 3 times, open it up and close it. Suddenly you've got 2 halves of a paperclip in your hands, and it has ceased to be able to perform its function. The same thing is true with road surfaces. We don't want to design a pavement that can only support 1 pass of this truck. That would be extremely embarrassing. But repeated loading, just like flipping that paperclip back and forth, you can do it a few times, 10, 1,000, 1,000,000, whatever, depends on how big you deflect it. Little tiny deflections on the paperclip, you could go for a long time, beyond your patience, before you would break it in half. Great big deflections on the paperclip, you do it 3 or 4 or 5 times and you got 2 halves. Same sort of thing here. That guy right there, that little automobile, is putting such a small deflection or such a small stress into the pavement that as far as the pavement is concerned, it doesn't even know the automobile is there. But this truck puts a great big deflection into the pavement, and you can't do it too many times before you wind up with a crack in the wheel path, as you see right there in the foreground. And so you have to design pavements so that they can support these kinds of loads, or these kinds of loads. Believe me, the folks that own these kind of trucks know what the law is, and they push it right up to the edge. And don't overlook these little guys. Just a little school bus, nothing but a whole bunch of 80-pound kids in it, doesn't matter. Rot. Notice that all that load's distributed over just a couple of wheels, but on the concrete truck and so on, you've got a lot more wheels, so it does make a difference. The principle here is to try and provide a sufficiently adequately strong base over the subgrade or basement soil so that the stress is dissipated. And you don't want to use a weak base material or you will deform it. And you'll see a heaving in the surface. That's evidence of either the failure can occur down in the subgrade or it can occur up in the base. But the principle is to transmit the tire load away from the stresses of the tire load, away from the subgrade. Now, that was a principle. Here's an actual factual laboratory demonstration of exactly the same thing. This simulates the pressure of a tire pushing in here. This was sand, dark-colored sand and light-colored sand, interbedded. And we just went away and started pushing. And notice, right here, you just follow my ruler, right out through there. All of that has been heaved up above the original surface. This has been pushed down. And out here, this material doesn't even know that that load was applied. The point is that there is a bowl or a basin within which failure occurs, and you want to be sure that the materials in this zone right here are adequately strong, and that's why we put pavements down. Now, the interlock between particles is one of the principal sources of strength, and generally speaking, for base course materials, you want to be sure you have enough little guys in between the big guys so that the big guys can't roll around, so that they can get good strength. One problem is clay. When you have clay, it's a platy particle, and if you've ever tried to walk around with a big stack of books, those are platy particles too. You have to push real hard together to get any strength, to be able to support a column of books on its side, for example. The same thing is true here, except imagine that as we add water, it provides a lubricating film, which changes the cohesion between the particles and makes them weak. And that's why we say that water is the enemy of base course materials. That's why specifications for gravels to go into roads usually always recommend that if you're going to put some kind of an impervious surface over the top, a seal coat, asphalt, whatever it might be, that you want to have less than 10% of the material passing the number 200 sieve. Less than 10% finer than 74 microns. Less than 10% in the silt and clay size particle range. And the reason for that is so as it does get moist, we won't have this problem of smooth, slippery grains sliding on one another. Because if you do, you wind up creating a much lower strength on this sliding surface, and as it gets wet, it becomes slippery, and the particles will slide by one another much more easily. Now, for relatively high volume roads, and I guess I would put the break point somewhere around 500 to 1,000 vehicles a day, you can certainly justify the expense of high-type pavements, asphalt concrete, typically hot plant mixed or treated, with a treated or untreated granular base. You can justify for the higher type highways Portland cement concrete. Again, a plant mixed material. It could have a treated or an untreated granular base. By treated, I mean having some kind of a binder in the base. For lower volume roads, typically we tend to use bituminous surface treatments, where we have an asphaltic binder with a crushed one-size aggregate. We will sometimes use a stabilized gravel or a stabilized base, stabilize it either with the dust palliative or with asphalt mixed in place. These are dust palletives, although they tend to do a little bit of cementing, the chlorides, or perhaps cement or lime fly ash, and usually to provide abrasion resistance, we would put a surface treatment on top of these kinds of stabilized materials. We even, to some extent, use unstabilized gravels. Crushed angular particles would be desirable. Clean would be desirable. Durable would be desirable. Durable? Well, the absence of shale, for one thing, would be in order to keep the shale out if possible. When you see this kind of a situation, here's an aggregate road, car going down the hill, you got two things that you ought to see right there. I guess the thing I'd like you to see first is the lack of safety. Heaven help the guy that's coming down the road behind this car and decides he wants to pass, because he doesn't have the slightest idea whether there's somebody coming on or not. Despite how, there's tremendous sight distance there. You can see forever, but you can't see around the car as you come up behind it. You wouldn't even know there was one there unless I told you it was there. So that's one thing you should see. I guess your pocketbook should twitch just a little bit too when you look at that slide, because what you see when you see all that cloud of dust is the road blowing away. And as the fine binder material goes away, then that releases the sand particles, and they wind up on the side of the road. As the sand particles go away, that releases the pea gravel, and it winds up in a berm on the side of the road. And eventually, you get the large particles in a berm over on the side of the road. That interferes with your cross-slope drainage, so that the water now is going down the road instead of over into the shoulder. You build it right to begin with, But over a period of time, with traffic and with the dust coming up, two things, safety problems and economic problems, come into play. How do you compensate for that? You either blade frequently or you apply some kind of a dust palliative to hold that down. Now there's a trade-off between the cost of applying a dust palliative, and this could be an asphaltic material, an oil material, a chloride material. It doesn't matter too much as long as you're within the law. There have been some restrictions put on the use, for example, of waste motor oils for very good reasons in terms of a dust palliative these days. It doesn't really matter too much what you put down as long as it's effective, does its job. The point is that there's a trade-off in the cost of applying that dust palliative and in the cost of replacing the gravel that's otherwise going to blow away because of the dust released. And furthermore, you can justify more than just the cost of replacement of gravel because of reduction of several associated problems. Improvement of safety for the traveling public, removal of the dust-borne diseases that the people alongside the road are subjected to, public relations and goodwill, that's worth something. So I would proselytize a bit on your aggregate surface roads, for the summertime at least, to use some kind of a dust palliative. Seal coats, this is a pretty good example of a seal coat placed on a local road. Here's another example of one that I don't like to see it this way. Look at all that extra stone. Now that costs money. Maybe not too much, $5, $10 a ton perhaps, something like that. But the point is that not only is it an economic waste, because there isn't any way you can get it back, too much stone was put on this seal coat. Now it's going to interfere with the crossroad drainage. You could come along with a motor grader and perhaps split it out for a shoulder, but it still is an economic waste. There's another aspect of it that I really am concerned about, and I don't think it leaps out at you directly. And that is, when you have all this extra stone, the way it got here was by coming across the road surface. When did it come across the road surface? It came across the road surface when the asphalt in this seal coat was relatively new, before the volatiles were out of it, when it was still soft and pliable, before it was doing the best job that it possibly could to hold the stone on that road. And so what do we have? We have tires together with these little chisels that are out there prying on the stone of the existing surface treatment, which you've just bought and paid for, trying its darndest to remove that stone off the surface. And so really, while you need a little bit of extra stone to keep from picking on tires and on the rollers that place this material, don't use this much extra. Maybe 4 or 5% would be perfectly adequate, so that you don't wind up trying to destroy the seal coat before it's placed down. Be concerned about putting it adequately wide, because if it's too narrow and the vehicle wheels are on the edge of the shoulder, the problem of raveling with a surface treatment is going to be very significant. And so you want to have good quality base underneath it to support the edge of that road. You want to have it wide enough so that vehicles aren't going to be trafficking directly on it. And if you do have a problem with edge raveling, then get out there and fix it before it ravels right into the middle of the road. If you have a road that looks like this, you don't need a PhD in civil engineering to know that this is a road that's settled and it's seen its day. And to come along here and just put another surface treatment on might very well be throwing good money after bad. The symptoms of the disease are on the surface, but the disease itself is down in the road base. And we really need to come in here, remove the frost-susceptible base material, or augment it by busting up the old seal coat and putting in new base to adequately support that surface treatment. Because all of this alligator cracking that you see right here comes for the same reason that the paperclip breaks apart, due to repeated flexure of ultimately causing a crack, and then subcracks. This is a main crack right there. Subcracks formed. Ultimately, all of this area in here will have cracks and will look like these areas right here. By the time it gets this bad, a tire ultimately pops one of these chunks out and some water sits in there. Before too long, the fines get pushed out and the chunks around it go away, and you have something that looks like this, a great big pothole. To just shovel some gravel back into that pothole, smooth things out, and come by with another surface treatment would be only marginally effective. It would not be the best way to spend the taxpayers' money. Had we got to this road before it began to crack and put another seal coat on there, then we would be spending the taxpayers' money wisely, because we would be maintaining the existing strength and augmenting it with additional section. And notice what was done right along in here sometime in the past to protect against the road edge raveling problem. Some kind of a cold mix, it looks like, was laid in there. That's good. That strengthened the edge of the road. I've talked a little bit about the basic principles of road engineering. I have a feeling that some of you might very well be sitting in your chair thinking, boy, all that Irwin has just said is going to cost me money. And how many of you are sitting there thinking that right now? One or two? Some of you are more honest than others. How many of you would buy off on the concept, gee, if my local governing body would give me the kind of money that it takes to do this sort of thing, I would be happy, I'd be sitting pretty, and my road system would look great? How many? Two hands from some people. Okay. If I just had the money, everything would be great. Okay. I want to, if I go away accomplishing anything, I guess I want to go away leaving you a little bit uncomfortable with that kind of thinking. So now if we can turn the lights off, I'm going to tell you something about that problem. I'll skip by the commercials on anti-potholes. Oh, I kind of like this one. I can't let this get by. That's a pothole, right? I won't give you the whole story, but that's a pothole. What's the inverse of a pothole? A pot hump. That's when some sucker keeps shoveling cold mix into that hole and won't make it go away. And he just puts good after bad. There's a base failure. Probably that's a subgrade failure with that wide a span to it. That's a 4-foot long stick there. Here's a base failure. You know, we have become conditioned. I'm speaking not just of us that are in the technical side of road building and the policy-making side of road building, but the public in general, because we're part of that group as well. The public in general has come to accept that this is what a road is going to look like before it's rehabilitated. That they don't expect to see a highway crew come out here until it's this bad, or maybe even a little bit worse, before anybody is going to come along and fix that road. And then ultimately, first they come by and they do some patching. Here's a pretty good example of that. You'll notice there's at least 3 generations of patches here. There's some real light gray, then there's some not quite so light gray, and then there's some that was just recently done. I have to chuckle at this. How did the guy that was out here doing this patching decide to place his blacktop here, but not here? Talk about a series of patches in search of a road. That's got to be it. You know, it's not just at the town level of government that this sort of thing happens. This is a state highway in New York State. If you look carefully, you'll see that they came along here and put what we fondly call a skin patch on the surface of this lane, and they stopped right there. But in the opposite lane, they went from here down to there somewhere. And there was literally a guy walking along in front of the paver, putting red marks on the road of where to start and where to stop with that paver. That's what we call an election day special in New York State. There was a new governor being elected that year. Here's what it looks like a year or two later. Water has gotten through a few cracks in the skin patch. Is that as out of focus as it looks like to me? That's a little better, I guess. When you're this close to the screen, everything looks out of focus, unfortunately. So tell me if things are out of focus. But the skin patch now has raveled in the wheel path. Pretty soon, that's going to be even worse. And that was sure a waste of taxpayers' money. Here's the fundamental principle that we're going to talk about. Whoop, wrong switch. Good? Thank you. The quality of a road is measured vertically on this scale by its roughness and, or its cost to operate on. Starts out when we've just rebuilt it in good condition. And then gradually over a period of time, and this is schematic. This says 5 years, 15 years, and so on. That could be 10 years to this point for a town road and 20 years for an interstate highway. So take this with a grain of salt. This is just to show you the relationship between quality and time. Notice the orange line comes down, keeps on going down, starts going down slow to begin with, and speeds up over a period of time. Now there's some point where driving on this road gets so bad that the public won't stand for it any longer, and so we come out and we reconstruct the road, put it back up into good condition, and it starts this cycle all over again. This is a fundamental principle. But in that movie that was shown this morning, it was mentioned that if you will catch a road and rehabilitate it right here as it goes from good to fair, a structural overlay, a couple inches of blacktop, will put it right back into good condition. It can start to deteriorate again, but it doesn't cost very much to do that by comparison with waiting till it gets down here where it's badly potholed, all broken up, the public is all angry, public relations have gone to hell in a handbasket, and now it's going to cost 10 times as much to rehabilitate that road as it does if you catch it in a timely fashion. And that 10 times is not due to inflation over that 5-year period. It's due to deterioration of the surface to where the only alternative becomes dig it up and throw it away and start over again. And if we could recognize the significance of this, we could make highway dollars stretch an awful lot further, so that the point, if I only had the money, I could do the job, would become a comment of the past, I think. The number of vehicles in this country is going up significantly over time. This is 1945, 1980. Notice that if you add up the trucks and the automobiles, 1982, we're talking about 150 million vehicles, 120 million automobiles, 30 million trucks or so. The number of registered drivers is going up. 1982, 150 million drivers. My Lord, if anybody's good at mathematics, that's one vehicle per driver. The ratio of trucks to automobiles in the United States is going up. It has, at least since the middle 1960s. That says we're using trucks more and more and more. The road mileage is pretty static. Here's state highway mileage, local and municipal, that'd be like cities and villages. Look way up there at the top, local, rural. Pretty steady quantities on the order of 2.4 million miles of road. If you add all of these together, we're at about 4 million miles of road in the United States. Did you know that 57% of the 4 million miles of road in the United States is aggregate surfaced? Now in 1970, it cost around $214,000 to rebuild a mile of good quality state highway kind of road, not a town road. In 1980, $600,000. That film that we showed quoted the figure of $670,000 per mile, and that's based on local figures in 1982. So we're talking about a lot of bucks here. Why that big change? Because the cost of doing business has gone up and up and up. In 1977, we had a cost index of 100. By 1981, we had a cost index on the order of 160, a 60% increase in 5 years' time in the cost of doing business. The thing I want you to see is, look at the long-term relationship here. 1945 to 1981, and nowhere really is there any significant regression of this curve. A little bit of a twitch here, a little bit of a twitch here, but by and large, over time, and this is a long time span, inflation has been with us, and folks, it's going to continue to be with us. So all of the gripes, grumbling, and otherwise about the increased price of asphalt, the increased price of equipment, is to no avail. We aren't going to stop inflation. We need to recognize that the price is going up, and our problems do not lie in the fact that things have gotten more expensive. Perhaps construction costs have gone up more rapidly than the overall consumer price index, but even that isn't relevant. This is a fact of life, something we have to deal with, and it does no good whatsoever to beat our gums on the topic. As a result, and now talking in terms of constant value dollars, as a result of national policy changes in the period around 1965, the amount of money that was available for capital improvement of highways in the United States as a whole, and I have checked many of the states in the Northeast, they all obey exactly the same pattern. There has been darn near a factor of 2 decrease in the amount of money spent per year for capital improvement of roads. The maintenance expenditure has gone up fairly steadily, and no big change in slope due to the failure to invest in reconstruction, interestingly enough. When we break that apart, however, things don't look so bad for some of us that are involved with local roads. If we look at the capital investment, we'll look at it per mile of road just to put it into perspective, and look at it on, but it wouldn't make any difference whether we did it per mile of road or not. The shape of these curves would be exactly the same. And look here. We're talking about state highways where the change has been perhaps in excess of a factor of 2 decrease. For the cities and villages around the country, there has been a bit of a decline, but not nearly as dramatic as that. And actually, there has been a bit of an increase in the slope of the local rural capital investment. But notice the significant difference in terms of the number of thousands of dollars per mile that are invested. And maybe it's pretty easy to see why state highways are in a heck of a lot better condition in many respects, because they're built to a higher standard. We spend more money per mile on them. Maintenance, broken apart, same sort of thing. At the local rural level, there really hasn't been a great decrease. At the municipal level, there has been. The state level, on the other hand, as a consequence of the tendency to disinvest in construction, there's been a significant increase in the amount of money that's had to be spent on maintenance. And if we look at the ratio of these, you'll notice that the maintenance cost per mile of road divided by the capital investment cost, or the percent of highway funds expended on maintenance, bottomed out about the time that the capital investment peaked out. And it bottomed out at about 15%, and is now up to about 30% of our state dollars are spent on maintenance. The other 70% is spent on capital construction. But still, the hurrier we go, the behinder we get at the local rural level, because about 55 to 60% of our dollars are spent on maintenance at the local rural level. And that's why I asked you that question earlier, how many of you were involved with maintenance, how many of you were involved with capital construction. And there was a very significant 4 to 6 ratio, I would say, in terms of the hand-waving that went on here. A little bit better situation in the urban areas than it is in the rural areas, but the point is that right now, at the state level, we're still spending an awful lot smaller portion of our total dollar on maintenance than we are on capital construction. At the rural level, we're spending an awful lot more. That tells you how much has been spent, what the policymakers were willing to spend, how much should be spent. These are some slides that were put together by the National Crushed Stone Association. I would point out that the numbers involve only the interstate, the arterial, and the collector level, and include no numbers on the local level. Part of the reason for that is that all of us at the local level are remiss in communicating what our needs are, I think. In 1976, it would have cost $11.2 billion to rehabilitate the highway system to the 1975 condition. Or that's about how much money per year needs to be spent to keep a constant condition. By 1980, that number had risen to $40 billion because of the decrease in the capital investment curve. We had been putting too little money into roads, and so now the deficiencies were growing. And it's estimated that by 1985, $119 billion need to be spent. In 1982, we spent for arterial collectors interstate $7.5 billion. So it shows that there's a whale of a shortfall between 119 that's going to be needed in a couple of years and $7.5 billion that's actually being spent. That's part of the reason why we see so doggone many potholes showing up on our main highway systems around the country. If we translate that $7.5 billion into dollars per vehicle, that 150 million vehicles, it winds up being about $48 per vehicle per year that we're spending in this country on capital improvement of our main highway system. Now, if we review some of the figures that have been splashed about before, potholes cause a wasting on the order of 113 gallons of fuel. They cause vehicle repairs on the order of $130 a year. They cause an increase in your automobile insurance bill on the order of $56 a year, and when you add those numbers together, we come up with $335 per vehicle per year. You multiply that by 150 million vehicles, you come up with the figure of $38 billion that's being tossed away due to driving on inadequate, poorly repaired roads. But compare this for a minute. We're spending $48 per vehicle, but out-of-pocket costs due to poor roads are wasting $335. And my point is, those of you that say, if I only had the money, I could do a better job, there's where to reach for it. Because as you do that better job, as we divert that money into road repairs, we wind up with a situation where that needless cost goes away. if you follow my logic. After we've got all our roads in good condition, the excess out-of-pocket cost for driving on poor quality roads is going to diminish, so that we don't have to wait for this kind of a condition to occur and then throw our hands up in the air and say, public, will you please give us the bucks? They are giving us, they're spending the money anyway. Their road user costs are going up as a consequence of the fact that road conditions are diminishing. Let's build some monuments to our good judgment, to the fact that we want to see good quality roads built. Get out there, correct the drainage problems, do good geometrics, sign the bridges, design the roads for the loads rather than lamenting the fact that trucks are too heavy. Remember that safety is an important consideration, and none of us want to wind up in this place. Recognize that it's possible to get good drainage, good roads, good signing, and keep the public happy, that the public is paying the money anyway. Now, if those of you in the back can't read the caption on this cartoon, it says, of course I've heard the expression countless times, but this is the first time I've ever seen one. It takes a second. I hope all of us can keep from getting our tail in a sling by virtue of what we do. And so as the sun slowly sinks into the west, let's turn on the lights and leave room for the next speaker. Thank you for your attention.